So you hear a medical test is, say, 90% accurate. And that sounds amazing, right? But what if I told you that simple number could be hiding a huge, maybe even a life or death mistake? Today, we are going to pull back the curtain on that single number. We're going to figure out how these tests really work, what kinds of mistakes they make, and why understanding that difference is one of the most important things you can know, whether you're in medicine or data science. Let's dive in.
Okay, so here's our game plan. First, we're going to see exactly why putting all your faith in accuracy is a big, big mistake. Then I'll introduce you to the hero of our story, a simple little grid called the confusion matrix. We'll break down its 4 parts, see how it unlocks a much smarter way to measure how well a test is doing, and finally, we'll talk about the tough choices that every single test forces us to make.
All right, let's start with the problem. Why is just saying a test is accurate not just unhelpful, but, well, kind of dangerous?
Imagine you see this headline. A brand new predictive model for a serious condition is 81% accurate. Now, your first gut reaction is probably, hey, that's not bad. That's a B-, maybe a solid B. But is it really? Is that the whole story?
Here's the catch. That 81% number tells us that it's wrong sometimes, but it tells us nothing about how it's wrong. You see, it treats all mistakes as equal. But in the real world, telling a perfectly healthy person they're sick is a very, very different kind of error than telling a sick person they're perfectly healthy. One causes stress and anxiety, the other could be catastrophic.
So there are really 2 fundamental ways a test can mess up. First, you've got a false positive. This is a type 1 error. It's when the test raises a false alarm. The courtroom analogy is perfect. It's like convicting an innocent person. Then you've got the other kind of mistake, a false negative, or a type 2 error. This is when the test misses something that is absolutely there. This is like letting a guilty person walk free. Now, which one is worse? Well, that totally depends on what's at stake. So how do we get past that one misleading number and actually see these different types of errors clearly? Well, we use a tool called the confusion matrix. And I know, it sounds a little intimidating, but it's really just a simple scorecard.
Yeah, seriously. Just think of it like a performance report card for your test. But instead of just one overall grade, it gives you 4 specific ones. It splits all the results into the correct yeses, the correct nos, the incorrect yeses, those are our false alarms, and the incorrect nos, which are those dangerous misses. This simple grid is the key to seeing the true story behind that accuracy number.
All right, enough theory. Let's make this real with a clinical example. What you're looking at right here is an actual confusion matrix from a model that was trying to predict heart disease in a group of 303 patients. The actual condition is on the left, and what the model predicted is up top. And remember, every single number in this grid represents a group of actual people.
Okay, let's zoom in and break this little 2x2 grid down quadrant by quadrant so we can really understand the story behind each of these numbers.
First up, in the bottom right, we have our true positives. These are the home runs. In our example, 111 people who actually had heart disease were correctly identified by the model. This is exactly what you want to see for these patients. They got the right diagnosis, a correct yes. Next, let's look at the top left. These are the true negatives. These are the correct rejections, if you will. We have 146 people who did not have heart disease, and the test correctly told them they were in the clear. For these folks, this is also a fantastic outcome, a correct and very reassuring no. Okay, now we get to the errors. In the top right corner, you'll see the false positives. These are the false alarms. 18 people who were actually healthy were incorrectly told that they had heart disease. Imagine the stress, the extra tests, the cost, all from a false alarm.
And finally, in the bottom left, we have what is often the most dangerous error of all, the false negatives. These are the misses. 28 people who actually had heart disease were told they were healthy. This is a really dangerous miss because these patients might not go on to get the treatment they desperately need.
So here's the magic. By laying out these 4 outcomes so clearly, the confusion matrix lets us move way beyond that simple accuracy number. It lets us calculate much more powerful metrics that show us the test's true character, its strengths, and its weaknesses.
Now we can use those 4 numbers, the true positives, true negatives, false positives, and false negatives, to ask much, much smarter questions. This table shows us how. Each of these metrics answers a really specific, really important clinical question. For now, let's just focus on the 2 big ones that are always in a tug of war: sensitivity and specificity.
Sensitivity, you'll sometimes hear it called recall, is all about not missing anyone. It basically asks, of all the people who really are sick, how many did our test actually catch? In this case, it was 80%. Now that's pretty good, but it also means we missed 20% of the sick people. A super-sensitive test is great for screening because if you get a negative result, you can be pretty darn sure you're in the clear.
Now, specificity is kind of the opposite. It's all about not raising false alarms. It asks, of all the people who are actually healthy, how many did our test correctly clear? Here, that number is 89%. So a test with really high specificity is fantastic for confirming a diagnosis, because if you get a positive result, you can be very confident that it's the real deal.
And this brings us to the final and maybe the most important piece of the puzzle. You see, no test is ever perfect. There is almost always this constant push and pull between these different metrics. You have to make a choice.
This quote right here from Principles of Data Science just nails it. If you tweak your test to make it more sensitive, to catch more sick people, you will almost always make it less specific, meaning you're going to get more false alarms. And if you do the opposite, if you make it more specific to avoid those false alarms, you're probably going to miss more real cases. It is a constant balancing act.
So the whole decision really boils down to the context. What's at stake? For, say, a really dangerous but treatable disease, you would want an incredibly sensitive screening test. You would rather deal with a few false alarms than miss a single real case. But for a test that leads to a really risky surgery, you would demand extremely high specificity. You need to be almost certain before you take that next step.
So I'll leave you with this question to think about. The next time you're faced with a test or a prediction of any kind, try to think beyond that single accuracy number. Ask yourself, what are the real-world consequences of being wrong? And which type of error, a false alarm or a dangerous miss, is the one you absolutely cannot afford to make? Because the answer to that question changes everything.